This video is going to talk about rational functions and some general characteristics of rational functions before next week when we get into graphing rational functions. So we start by looking at the reciprocal function y equals 1 over x, which you'll see graphed over here. And when we look at the domain of it, so going from left to right, we see that there's something happening from negative infinity to 0, and then a break, and then something happening from 0 to infinity. So the question, what happens at x equals 0? Well, if we look at y equals 1 over x, in general, when we have a denominator, we talk about whatever makes it equal to 0, because dividing by 0 makes something undefined. So whatever makes that denominator equal to 0 is what our function cannot equal, what x cannot equal. So for this, y equals 1 over x, we say that x cannot equal 0. So at x equals 0, what we have is this nice vertical asymptote, because our function, x can be anything to the left of it and anything to the right of it, but it cannot equal 0. So we say that we have a vertical asymptote at x equals 0. And then the range of our function goes from negative infinity to 0, and then again from 0 to infinity. So we also have this nice horizontal asymptote at y equals 0. And so as x approaches negative infinity, so as we go over here and x approaches negative infinity, our f of x is approaching 0, and as x approaches positive infinity to the right, our f of x is approaching 0. Okay, so the first thing that we look at for a rational function f of x is equal to g of x over h of x, with the denominator h of x not being equal to 0, is we talk about the vertical asymptotes. So it says here, vertical asymptotes are located at the zeros of the denominator. So just like the one we looked at above, where we just had x in our denominator, so x cannot be 0, anything that's in our denominator, that anything that we have to set equal to 0 and figure out where our vertical asymptotes are going to be. So to find vertical asymptotes, it says set the denominator equal to 0 and solve. And there can be more than one, so there can be many vertical asymptotes. So for example 1, where we have x over 2x minus 1, I'm taking this, 2x minus 1, setting it equal to 0, and we get that x is 1/2. So we would have a vertical asymptote when x is 1/2. For b, I've got x squared minus 9 over x squared minus 7x plus 12. So first thing that I have to do is factor this and simplify. So my numerator factors into x plus 3 times x minus 3, and the denominator factors into x minus 4 times x minus 3. So if you notice, we've got a common factor in both our numerator and our denominator, so those are going to cancel, and we'll talk a little bit more on the next page about what happens when we have that. But right now, what we're left with is x plus 3 over x minus 4. So in our denominator, we have x minus 4. So if I set that equal to 0, I get that part B has a vertical asymptote at x equals 4. Okay, so that's for vertical asymptotes. They come from the denominator. Horizontal and oblique asymptotes, also known as end behavior asymptotes, so the one that we had up here, that was our y equals 0, they come from looking at the degrees of the numerator in comparison with the degree of the denominator. So if the degree of the numerator is less than the degree of the denominator, and I like to write that as little d for degree, and then a big N for numerator, is less than the degree of the denominator, then we're going to have a horizontal asymptote at y equals 0. The degree of the numerator is equal to the degree of the denominator, then we're going to have a horizontal asymptote at y equals leading coefficient, or a, divided by leading coefficient, or a. So for this example here, we have f of x equals 4x minus 1 over 2x plus 3. So the leading coefficient of the numerator is a 4. The leading coefficient of the denominator is a 2. So 4 divided by 2 gives me a horizontal asymptote at y equals 2. And then finally, if the degree of the numerator is greater than the degree of the denominator, we're going to have an oblique asymptote, which we'll find using long or synthetic division. And we'll talk about that on the next page. Okay, so example 2, I want you to determine the horizontal or oblique asymptote of each of the following. So go ahead and pause this video and see if you can figure out for A, B, and C whether they have a horizontal or oblique asymptote and what the asymptote is. And then when you're done, go ahead and press play again and you'll check your answers. So for example 2A, the degree of the numerator, which is 1, is less than the degree of the denominator. So when the degree of the numerator is less than the degree of the denominator, we're going to have a horizontal asymptote at y equals 0. For part B, the degree of the numerator, which is 1, is equal to the degree of the denominator, which is also 1. So we're going to have a horizontal asymptote at leading coefficient divided by leading coefficient. So that's just a 1 divided by a 1. So a horizontal asymptote at y equals 1. And then for part C, here the degree of the numerator is 2, and the degree of the denominator is 1. So the degree of the numerator is greater than the degree of the denominator. So this tells us that we're going to have an oblique asymptote. To find that, we're going to use synthetic division. So I'm going to be dividing by x minus 3. And we have 2x squared plus 3x minus 2. So when I carry down my 2, 2 times 3, 6. 3 plus 6 is 9. 9 times 3 is 27. And negative 2 plus 27 is 25. So we disregard the remainder, but our oblique asymptote is going to be at y equals 2x plus 9. Okay. Now we can kind of go back and look at the scenario we looked at on the other page where I canceled out my factors of x minus 3 over x minus 3. So whenever I have a function where they share a common factor, we can simplify by canceling that common factor, and then the factor that we're canceling is our whole, our removable discontinuity. It's located at that x value. So once we find the x, we then find the y by substituting the x value into the simplified function. So let's look at an example together. In example 3a, if I factor my numerator, we're looking for two numbers that multiply to negative 2 and add up to negative 1. So that's x plus 1 times x minus 2 over x minus 2. And I notice that here I've got common factors, right? X minus 2 over x minus 2. So I'm going to cancel those out. And that tells me that my whole is at the x coordinate of 2. And that I find the y coordinate by plugging 2 in to what's left, right? So once I cancel those out, all I'm left with is x plus 1. So when I plug the 2 back in there, 2 plus 1 is 3. So my whole is at 2, 3. Okay, so why don't you pause the video now, go ahead and try B and C, and then you can press play once you've tried those, and you can check your answers. Okay, so for part B, if I factor my numerator, that's x plus 1 times x minus 3 over the denominator of x minus 3. And again, I've got common factors. I've got x minus 3 over x minus 3. So I'm going to cancel those out, and therefore we will have a whole at 3, comma, and again I'm going to look for my simplified function, which is just x plus 1 again. So if I plug 3 in for x, 3 plus 1 is 4. And then finally, for part C, my numerator, I can first factor an x out, and then I'm left with x squared plus 5x plus 6, which factors into x plus 2 times x plus 3. And my denominator, I can factor an x out, and then I'm left with x squared minus 9, my difference of squares. X minus 3 times x plus 3. So for this one, I actually have two wholes. I've got x over x and x plus 3 over x plus 3. So I'm going to have a whole at 0, comma something, and at negative 3, comma something. So when I plug 0 in to what's left, right, so once I cross those out, I'm left with x plus 2 over x minus 3. So if I plug 0 in, I have 2 over negative 3. So it's 0, negative 2 thirds. And when I plug negative 3 in, I have negative 3 plus 2, which is negative 1 over negative 3 minus 3, negative 6. So negative 1 over negative 6 is a positive 1/6. So those would be my two wholes for part C. And then the final thing that we're going to talk about today with characteristics of our rational functions is intercepts. I can have x-intercepts and I can have y-intercepts. So to find the x-intercepts, they are just the zeros of the numerator. Right, so we set our numerator equal to 0 and we solve. And then to find a y-intercept, just like we did for polynomial functions, I'm just going to plug in 0 for x and find y. So for example, for a, it's already been factored for me. So to get my x-intercepts, I'm going to set x minus 1 equal to 0 and not y. And I'm going to set x plus 2 equal to 0. So we have x equals 1 and x equals negative 2. So our x-intercepts are 1, comma 0 and negative 2, 0. And then to get my y-intercept, I'm plugging in 0 for x. So that's 0 minus 1 times 0 plus 2 over 0 minus 4. So that is negative 1 times 2 is negative 2 over negative 4, which is 1/2. So our y-intercept is 0, comma 1/2. All right, now go ahead and try B. So press pause and try B, and then go ahead and press play when you are ready to check it. For part B, we have to factor our numerator first. So that factors into x plus 1 times x minus 5 over x. So our x-intercepts, which come from the numerator, I'm going to set x plus 1 equal to 0 and x minus 5 equal to 0. So we have x equals negative 1 and x equals 5. So our x-intercepts are at negative 1, 0 and 5, 0. And then our y-intercept comes from plugging in 0 for x. So we have 0 plus 1 times 0 minus 5 over 0. But when I divide by 0, I'm getting undefined. And the reason for that is if I look up here, if we remember where our vertical asymptotes come from, the vertical asymptotes happen where the denominator, what makes the denominator equal to 0. So there would be a vertical asymptote at x equals 0, so there are no y-intercepts. And that's it. So we'll look at graphing rational functions next week, but this should be hopefully helpful in just identifying some of the characteristics of rational functions.